Hello. Today we're going to take a look at graphs of rational functions, this time focusing on x and y intercepts. So I'm starting on page 26 in your rational functions notes packet. And we're going to start with a little sort of refresher of everything that we've seen so far and kind of add in those new topics, those x and y intercepts. So as we're talking about graphs of rational functions, we've had a couple key features that we focused on, namely those removable discontinuities, or holes, we've called them, and vertical asymptotes. We can also have something called horizontal asymptotes. We're not going to look at finding those algebraically, but we will take a look at them in the graph. So on my graph here of my rational function, I don't see any holes. I don't see anywhere where I have a little open circle on my graph. So it looks to me like we don't see or have any removable discontinuities for this function. But we do have a vertical asymptote. It looks to be right about here. I've got this kind of split in my graph. So I've got a vertical asymptote, and it looks like x equals -2. Now, we also can see another split in our graph this way, right about here. Since this line is horizontal, this is what we would call a horizontal asymptote. And we're not going to talk about finding these algebraically. We'll just stick with those vertical asymptotes. But horizontal asymptotes do exist. This one looks like it's about y equals -1/2, estimating from my graph. I do have a horizontal asymptote there as well. We can also have what are called slant asymptotes, where they're sort of diagonal through my graph, based on the shape here where I'm approaching this vertical line and approaching this horizontal line. It looks to me like we just have vertical and horizontal asymptotes. Slant asymptotes are a thing. And then let's talk about those other key features that we've cared about for our other graphs, x and y intercepts. So remember, an x-intercept is where we cross the x-axis. It looks like we have an x-intercept right here at -9. Since I have a horizontal asymptote, I'm not going to have another x-intercept over here because my graph, this portion of my graph, won't be able to cross that asymptote. And then if I look for any y-intercepts, I've got one right here. And that looks like it's at y equals -2. I won't have any y asymptotes from this portion of my graph because I have this vertical asymptote here, and this section of my graph won't ever be able to cross it, so I won't have any y-intercepts there. Now, we talked about finding vertical asymptotes and holes algebraically. We looked at finding those excluded values by factoring the bottom of my function. Remember, if it's reducible, it's removable. So those factors that I could reduce give me holes. The ones I can't give me asymptotes. So today we're going to shift our focus to being able to find those x and y intercepts algebraically. So on the next page, page 27, we've got a function here, and we're going to find the x and y intercepts for this function. So I'm going to start by finding the y-intercept. This is probably the easier of the two. So remember, the y-intercept happens when x is 0. So if I go back to my graph here, the y-intercept happens when our x value is 0. So to find a y-intercept, we're going to substitute in 0 for x anywhere I see it in my function. So my y-intercept would be 0 plus 10 over 0 minus 5. And then we just simplify. Whatever we have in our function to simplify, we'll simplify. So I would have y equals 10 over -5. I can reduce that. 10 divided by -5 would be -2. So we have a y-intercept at -2. So our y-intercept would be at 0, -2. Now to find our x-intercepts, we have to make sure that we're not accidentally identifying a hole as an x-intercept. So what I need to do is make sure that I reduce, okay? Reduce before we try to find x-intercepts. So as I look at my function, x plus 10 over x minus 5, these are not reducible because these are not the same. So I can't reduce this at all. I don't have any factors that are common to the top and the bottom. So for this problem, I can go ahead and substitute in 0 for y, because remember, the x-intercept happens when that y value is 0. So what I'm going to do is come over to my function and plug in 0 for my y value. And now our goal is to solve for x. Okay? So up here, we solved for y. We plugged in 0 for x and solved for y. That gave us the y-intercept. Now we're plugging in 0 for y, and we need to solve for x. So as I'm looking to solve for x on this thing, what I want to do is not have this fraction over here on the right-hand side anymore. I don't want to be dividing by anything. So what we're going to do is multiply both sides by x minus 5. Okay. My goal with that is to get this x minus 5 out of the bottom here so we don't have a fraction anymore. Another way to think about this is that we're cross multiplying. So this is going to be the same as if I think about this as cross multiplying. So two ways to think about the same work. So if I wrote that 0 as 0 over 1, so it looks like a fraction equals a fraction, and then I cross multiply, I end up with the same thing, 0 times x minus 5, and then 1 times x plus 10. This would always be 1, right? 1 times that top is just going to be the top. So either way, we end up with 0 times x minus 5, which is just 0. 0 times anything is just 0, equals whatever was on top here. So x plus 10 in this case. Now I want to finish solving for x, so we're going to move that 10 to the other side, and we get x equals negative 10. So I have an x-intercept at negative 10, comma 0. I could check these on my calculator by graphing my original function and finding those x and y intercepts. Remember, x-intercepts to find, that's the 0 function. When I choose menu and analyze graph, I'm looking for the 0. And then for my y-intercept, you can find that from your table or a graph trace. Okay, let's take a look at a few more examples. So on the next page, we've got another function here, x squared plus 4 over x squared minus 2. Now, as I'm looking at my function here, since I have x squareds, I want to be able to factor this so I can reduce. X squared plus 4, it's two terms. I don't have a GCF here. So what I want to do is factor this as a difference of squares, but it's not a difference, it's a sum here. So this is not going to factor into real numbers. So we're going to go ahead and leave that on top. On the bottom, x squared minus 2. Again, two terms. I've got a binomial. I don't have a GCF to pull out here. So again, I want to factor this as a difference of squares, but 2 is not a perfect square. So I'm not going to get integer factors here, real number factors. So since these aren't going to factor into real rational numbers, we will get real numbers on the bottom, but not rational numbers. Since I can't factor these into real rational numbers, we're not going to be able to reduce either of these factors. So that will come into play for our x-intercepts here at the bottom. For our y-intercept, remember we're going to plug 0 in for every x. So y equals 0 squared plus 4 over 0 squared minus 2. 0 squared is just 0. So I would get y equals 4 over negative 2. 4 divided by negative 2 is just negative 2. So I have a y-intercept at 0, comma, negative 2. Now for my x-intercepts, remember I want to reduce first. We talked just a minute ago about how we won't be able to reduce anything here. So now I'm going to go ahead and set y equals 0 and solve for x. Now, same idea here. However you think of this is fine. If you think about multiplying both sides by the denominator to get it out of here, to get it to reduce, that's fine. I'm going to write this as cross multiplying. So when I cross multiply, I would have 1 times x squared plus 4 equals 0 times x squared minus 2. 1 times anything is just that thing. And then 0 times anything is just 0. So I get x squared plus 4 equals 0. From here, I want to solve for x. So I'm going to move that 4 to the other side. And I get x squared equals negative 4. And since I have x squared by itself, I can take a square root. So I get x equals plus or minus. Remember, anytime you take a square root, plus or minus. And then since I'm taking the square root of a negative number, I know I'm going to have an I. And then 4, 2 times 2. So I would have 2i here. X equals plus or minus 2i. Now, if we're talking about our Cartesian coordinate plane, that coordinate plane we're used to seeing when we graph, there aren't i's on there, right? It's not a complex plane. So because all of my options here are imaginary, that means I will have no real x-intercepts. Okay, no real x-intercepts. So if I graph this, what I'm going to see is that I don't have any place where my graph crosses or touches the x-axis. Okay, and we can actually pull up our calculator and check that. So I'm going to grab up my calculator here. I've got an old graph here. Put that away, and I'm going to go ahead and get rid of that so we can graph this function to take a look and see. So let's go ahead and get our fraction set up there, and we've got x squared plus 4 over x squared minus 2. And I can see I have a horizontal asymptote here, right? And a couple vertical asymptotes as well. But I have a horizontal asymptote here right on the x-axis. So I'm not ever going to have any x-intercepts, which is why we found no real x-intercepts in our problem. Okay, we're going to take a look at one more example together for today. So if you would for me, turn the page to page 29, and we've got one more function that we're going to take a look at. So x plus 4 over x squared plus 6x plus 8. We're going to find that y-intercept first, so we're going to put 0 in for all of the x's. So y equals 0 plus 4 over 0 squared plus 6 times 0 plus 8. Okay, and then we're going to simplify. So 0 plus 4 is 4. 0 squared is 0, plus 6 times 0 is 0, plus 8. Just leaves me with 8 on the bottom. And then 4 over 8 would reduce to 1/2. So we have a y-intercept at 0, 1/2. And then to find our x-intercepts, again, we want to make sure we reduce. So going back to my function here, I can factor the bottom. I would use AC method here, and we would get x plus 4 times x plus 2. Now I see I have x plus 4 on the top and a factor of x plus 4 on the bottom, so I could actually reduce those. So my reduced function would be 1 over x plus 2. So I want to go ahead and plug in 0 for y in my reduced function. So 0 equals 1 over x plus 2. And then from here, I'm going to cross multiply. So I'm going to write that as over 1. And I would get 0 times x plus 2 equals 1 times 1. So 0 times anything is 0. And then 1 times 1 is 1. And I get something weird here. This is false. 0 is not equal to 1. So that, again, is going to tell me that I don't actually have any real x-intercepts here. If I solve and I get something that's not true, I have no more x's and 0 is not equal to 1, that means I'm not going to have any real x-intercepts. Now, let's take a look at what would happen if I had not reduced this function. So if I kept this as x plus 4 over x squared plus 6x plus 8. Let's look at what would happen here. If I go to cross multiply, I would get 0 times the bottom, which would just be 0, equals 1 times the top, which would be x plus 4. So if I didn't reduce, I would end up with 0 equals x plus 4. Now to get x by itself, I would move that 4 over, and I would have an x-intercept here at -4. Now here's the problem. we know because this factor reduced that x equals -4 is actually a whole. So if I check my graph, let's take a look at this here. If I check my graph, we want to make sure that we've correctly classified that point and that we actually do not have any real x-intercepts. I'm going to go ahead and change this function to match what we have on our paper. So x plus 4 over x squared plus 6x plus 8. So here's our function. And it looks kind of like maybe an asymptote, a horizontal one at 0. So that makes me think we're probably not going to have any x-intercepts. Although we did find that -4. If I didn't reduce, I would have gotten an x-intercept at -4. So let's take a look at our table. Control T to pull up that table. And then let's go to -4 here. Undefined. So that means I do not have an x-intercept at -4. If it were an x-intercept, it would say 0 here. But since it says undefined, it's a whole, okay, which we knew because that was reducible. And then while we're here, let's go ahead and double check our y-intercept. So the y-intercept happens when x is 0, and I got 0.5 as that y value. If I go back to my paper here, we got our y-intercept to be 1/2, which would be 0.5. Okay, so you can use your calculator to check these with your graph, and just make sure when you go to find those x-intercepts that you reduce before you set y equal to 0.